A few weeks ago, we completed a significance test to consider whether the proportion of one color of regular Skittles was different from 20%. And we're going to use those same data to reconsider a different question. Do these data give us evidence that the proportions for the 5 Skittle colors are not the same in the population? So remember, there are 5 colors, so that means 20% of each color. So the proportions for the Skittle colors are all the same. That would be the null hypothesis, 20% each. So we're looking for evidence then of the alternative, evidence that the proportion for the 5 Skittle colors are not the same in the population. So the alternative, the proportions for the Skittle colors are not all 20%. So understand, we've done 1 proportion z tests, we've done 2 proportion z tests. Well, here there are 5 proportions. So instead of trying to write a null and an alternative hypothesis by using literally all 5 parameters, the proportion for red, the proportion for orange, the proportion for green, it's much simpler to write this out in words. So if nothing special is going on, we really get 20% of each color. That's the null hypothesis. So the alternative then is that we get something different from that. So there are so many possible alternatives that it's not even possible to write all of the possibilities. It's much easier to write it in words. So the actual counts that we had, the sample that I want to use, we observed 77 red, 60 orange, 66 green, 92 yellow, 84 purple. This is a total of 379 Skittles in our sample. So remember, when we do significance tests, we always start by assuming that the null hypothesis is true. So if HO up here, if HO is true, if the null hypothesis is true, then we get what are called expected counts. We can calculate here the expected counts. So notice we have 379. If we take 379 times the percentage that we have in the null hypothesis, 20% each, 379 times 20%, that gives us 75.8. So if in fact the null hypothesis is true, we would expect the count of red and orange and green and yellow and purple Skittles, we would expect all of them to be 75.8. Again, our null hypothesis is that each color will happen 20% of the time. So if each color represents 20% of the population of Skittles, in our total of 379 Skittles, we should get 75.8 of each. For the expected counts, it's important to leave them as decimals. They are not the actual counts that we've observed, and you don't want to confuse them with the actual counts. This is what we would expect. So this test is called a chi-squared test for goodness of fit. It does not use a z-score. It does not use a t-score. It uses what's called the chi-squared statistic. I will show you that in just a few minutes. But it has 2 primary conditions that are important to check. Of course, fundamentally, we have to have a random sample. So we need to believe that our bag of Skittles that I bought it at Kroger, and then we brought it here to class. So we have to believe that this is a random sample from the Skittles population. So the other condition that we have to check, we have to make sure that essentially our sample size is large enough so that we're getting at least 5 of each of the expected counts. So all of the expected counts, I want them all to be at least 5, and we have no problem with that. So the counts condition, what's important is that all of our expected counts, not the actual ones, but all of the expected counts should be greater than or equal to 5. And they most certainly are. So we can proceed. The name of this test, we should always name the test. This is a chi-squared. So chi is written C-H-I, but this is the capital Greek letter chi. It looks like a sort of a curlicue X. This is the chi-squared goodness of fit test. When we say goodness of fit test, what we mean is how well do our data follow? How well do our data fit what we have assumed in the null hypothesis? How well do our data fit this hypothesis that each color will occur 20% of the time? That's what we mean by goodness of fit. And in terms of the degrees of freedom, the degrees of freedom are the number of categories that we have. So in this case, we have 5 colors. Take away 1. So the idea being 4 of these colors, 4 of those values are free to vary. 4 of those can be any counts that we like. However, the 5th and final one is not free because it has to be whatever's required in order to create the total sample size. So the degrees of freedom are 5 minus 1, in this case 4. So let's talk about the statistic that we're going to calculate. The calculator will find the statistic and the p-value for you, but let's talk about what the statistic actually represents. So if we're interested in deciding, we're going to assume the null hypothesis is true, and then we're going to compare our actual counts to what we expect. So notice sometimes the actual and the expected count are quite close. Sometimes the actual and the expected count are quite far away. So the closer that those are, we're going to get a statistic that's relatively small. And that won't give us much evidence to reject the null hypothesis. The farther apart these counts are, that suggests that maybe we should be rejecting the null hypothesis in favor of the alternative. So what we need to do then is look at those differences first of all. So for the red Skittles, the observed count is 77, the expected count is 75.8. So for the orange Skittles, the observed count is 60, the expected count is 75.8. The expecteds will always be 75.8 in this example. So for green, 66 is observed, 75.8 was expected. For yellow, 92 observed, 75.8 expected. And then for purple, 84 observed, 75.8 expected. So the first thing that you do in order to create this statistic is you look at the difference between the observed and the expected counts. We call those O and E. Now notice some of those will be positive, some of those will be negative, and we've seen this problem before. We don't want to just add all of these differences in order to avoid the negatives and the positives canceling. It's a good idea to square all of these. That's what the chi-squared statistic requires. That's why it's squared. So we're going to take our observed minus our expected counts and we're going to square them. So these are the squared differences between the observed and the expected counts. Now, all of these are then weighted by the expected counts. So all of our expected counts are the same. So we're going to divide everything by 75.8. So again, whatever the expected count is, we're going to divide by that expected count. In this example, they're all the same. So then we take the sum. So we simply add up all of these together. And this creates for us our chi-squared statistic. So this expression over here in general is what we call the chi-squared statistic. It is the sum of the observed minus the expected counts. We square those, and we divide by the expected counts. So we can calculate it by hand, or we can let the calculator do the work for us. So one of the things that we'll need to do regardless is get the data into list 1 and list 2. So I suggest that in your calculator, we'll go to Stat and Edit. So in list 1, I always recommend putting the actual counts in list 1. So our actual counts are 77, 60, 66, 92, and 84. The observed counts, rather the expected counts, I would put those into list 2, and they're all 75.8. So if we wanted to on the home screen, we could find the chi-squared statistic. So all we have to do is take our values in list 1, subtract from them the values in list 2, that's the observed minus the expected counts. We should square that, divide by what's expected, that's in list 2. Then I'll store it into list 3. Of course, I still need to take the sum of that. So if you go to second stat, you can go over to math, and you can take the sum of list 3. So our chi-squared statistic should be about 8.9. Of course, I really don't want you to calculate it by hand. I don't want you to calculate the p-value by hand. We could. I want you to see the structure of the chi-squared statistic. That's why I wrote it out here. But fundamentally, I would encourage you to have your calculator do it. So let's let our calculator do the work for us, and let's talk about what the p-value is going to look like then. Understand, the chi-squared statistic has to be or have a distribution that's skewed to the right, because notice, whatever we do here, again, we've already found that this value is about 8.9. So understand, whatever we do here, the chi-squared statistic is always positive. So if the differences are smaller, if the differences between the observed and the expected counts, if those are smaller in all of these values here, when I add them up, I'm going to get a relatively small chi-squared statistic. So a relatively small chi-squared statistic isn't going to give me much evidence to reject the null hypothesis, because the observed and the expected counts are going to look quite similar. We should get a relatively large p-value in that case. So we can't reject the null hypothesis. As the chi-squared statistic gets larger, that happens when the observed and the expected counts are farther apart. As this statistic gets larger, our p-value should get smaller in order to give us the opportunity to reject the null hypothesis. So the shape of the chi-squared distribution is skewed to the right. So what we need to do then is find the likelihood of a chi-squared statistic that is 8.9 or larger. So we'll put 8.9 here. What we are trying to find then is this probability right here. This is going to be our p-value. And we should let the calculator calculate that p-value for us. So there are two ways to do it. If the data are in list 1, if the observed counts are in list 1 and the expected counts are in list 2, one of the things that you can do is use the chi-squared GOF test command. So if you press stat and go to tests and scroll down, you will see a command that says chi-squared GOF test. If you highlight that and press enter, notice the observed counts we have in list 1, the expected counts are in list 2. We have 4 degrees of freedom. Literally all you have to do is highlight calculate, press enter. Try that again. Highlight calculate and press enter. So there's the statistic that we already had. There's the 8.9, and there's our p-value of about 0.063. So that gives us what we need. And again, our statistic, if I round it to, if you will, 2 decimal places, it's 8.93. So the statistic, chi-squared, is about 8.93. The p-value that we got is approximately 0.063. And then we can conclude this test just like any other test. Now, if you don't have the chi-squared goodness of fit command, I put a program on your calculator where you can do the same thing. Of course, you need the observed counts in list 1. and then you need the expected counts in list 2. Then, this is mostly for the people that have the TI-83s. If you press the program button, the program you want to run is titled chi-square. So highlight it and press enter twice. It'll ask you for the degrees of freedom first. That's 4. Highlight it and press enter. It assumes that the observed counts are in list 1 and the expected counts are in list 2. It gives you the exact same thing, 8.93, 0.063 for your p-value. So either way, we're ready to interpret this. So this p-value is larger than, we'll use a significance level, which is 5%, a typical significance level. So even though this is a relatively small p-value, it's simply still larger than our 5% boundary. So we don't have strong enough evidence to reject the null hypothesis here. So with a p-value of approximately 0.063, which is greater than our level of significance alpha of 5%, we fail to reject the null hypothesis. And truly, you are better off than copying the way that you wrote down the alternative hypothesis at the top. So we do not have strong enough evidence to support the alternative hypothesis. That's essentially all we need to conclude. So we don't have strong enough evidence. We don't have strong enough evidence to conclude. And I'll copy the alternative hypothesis. To conclude, the proportions for the Skittle colors are different from 20% each, are not all 20%. So just like all of our significance tests, there are 4 things to do. We have a null and an alternative hypothesis. So we have conditions to check. Those conditions include randomness and then the counts condition. So it's important to calculate your expected counts by using your null hypothesis value and your sample size. So our sample size times 20% for each gives us our expected counts. So third, we have a test name. You should write down your degrees of freedom, your statistic, and your p-value. And then last, you simply need to write your conclusion, just like we conclude all of our significance tests. This is the chi-squared goodness of fit test.